वेलकम टू वीलर्न में आपका स्वागत है। सब्जेक्ट ऑपरेशन रिसर्च सेशन नंबर 3। टॉपिक टू बी कवर्ड इन दिस सेशन: सिंप्लेक्स मेथड फॉर लीनियर प्रोग्रामिंग, सिंप्लेक्स मेथड कॉन्सेप्ट एंड एग्जांपल्स, टू फेस्ड मेथड्स एंड इट्स एग्जांपल्स। नाउ example number 1, inspector problems. Assume that it is desired to hire some inspectors for monitoring a production line. A total amount of 1800 species of products are manufactured every day. 8 working hours, while 2 grades of inspectors can be found. Maximum 8 grade A inspector and 10 grade B inspector are available from the job market. Grade A inspectors can check 25 species per hour with an accuracy of 98%. Grade B inspectors can check 15 species per hour with an accuracy of 95%. Note that each error cost of $2 per species. The wage of a grade A inspector is $4 per hour and the wage of a grade B inspector is $3 per hour. What is the optimum policy for hiring the inspectors? And now problem formulation. Assume that the X1 grade A inspectors and X2 grade B inspectors are hired, then total cost to be minimized as 4 into 8 multiply X1 plus 3 into 8 multiply X2 plus 25 into 8 multiply 0.02 multiply 2 X1 plus 15.8 multiply 0.05 into 2 X2, which is equal to 40 X1 plus 36 X2. Manufacturing constant are as follows: 25 multiply 8 X1 plus 15 multiply 8 X2 greater than equal to 1, and second constant is 200 X1 plus 120 X2, which is equal to which greater than equal to 1800. Number of inspectors available: 0 less than X1 less than 8 and 0 less than X2 less than 10. इस तरह से हम इसको ग्राफिकल इसका सॉल्यूशन कर सकते हैं। और ग्राफिकल सॉल्यूशन करने के लिए हमें क्या करना है, 40 जैसे हमारी दो कंस्टेंट हैं। पहली कंस्टेंट आपकी ये है 200 X1 प्लस 100 X2 ग्रेटर देन इक्वल टू 1800। तो हम इसमें क्या करेंगे, पुट X1 इक्वल टू 0 टू गेटिंग द वैल्यू ऑफ X2। इसी तरह से दूसरे कंस्टेंट में भी एक कंस्टेंट आपकी ये है, इसके अंदर भी पुट X2 इक्वल टू 0 टू गेटिंग द वैल्यू ऑफ X1। इस तरह से जो है हम ऑर्डिनेंस इसके निकाल लेते हैं और उसके बाद में प्लॉट कर देते हैं। एंड नाउ थ्योरम प्रॉपर्टीज: इफ देयर एग्जिस्ट एन ऑप्टिमल सॉल्यूशन टू एलपी, then at least one of the corner point of the feasible region will always qualify to be an optimal solution. Special cases: alternate solutions, non-unique solution, maximum x1 plus 2x2, subject to x1 plus 2x2 less than equal to 10, x1 plus x2 less greater than equal to 1 and x2 less than equal to 4. तो इस तरह से जैसे मैंने आपको अभी बताया कि हम इसके अंदर क्या करेंगे, x1 की जगह 0 पुट करेंगे टू गेटिंग द वैल्यू ऑफ x2 एक बार, और दूसरी बार जो है x2 की जगह 0 पुट करके x1 की वैल्यू इक्वेशन 1 के अंदर दो वैल्यूज आपके पास आ जाएंगी। सेम एज नेक्स्ट में x1 इक्वल टू 0, देन टू फाइंड वैल्यू ऑफ x1 एंड देन अगेन पुट x2 इक्वल टू 0 टू गेटिंग द वैल्यू ऑफ x1। तो इस तरह से तीनों की वैल्यू हम निकाल करके और ऐसे करके पॉइंट प्लॉट कर लेंगे और उनको मीट करा देंगे। तो इस तरह का जो ग्राफ आपके सामने आ जाएगा। स्पेशल केसेस कंटिन्यूड: अनबाउंडेड ऑप्टिमा, a system has a feasible region with open boundaries such that the optima may appear at the infinity. Example for the previous example: in case constant is x1 plus 2x2 less than equal to 10 is not given, then moving far away from the origin increases the objective functions x1 plus 2x2 and the maximum z would be infinity. unbounded optimum like this one. Then example 2, student 5. The RIT student run microelectronic fabrication facilities is taking orders for 4 indigenously development of ASIC chip that can be used in one touch sensors, $6 per 4 hours, 1 hours, M1 hours, V30, and second LCD 10 hours, second 9 hours, M1 per hours, and V40. 3 pressure sensors, $9, S7 hours, M3 hours, V20, and fourth constant is controllers, $20, S10 hours, M8 hours, and V10 hours. So constant is students HR less than equal to 600, machines hours less than equal to 420, and space available is less than 800. So the LP problems: maximum 6x1 plus 10x2 plus 9x3 plus 20x4 subject to 4x1 plus 9x2 plus 7x3 plus 10x4 less than equal to 600. Then x1 plus x2 plus 3x3 plus 8x4 less than equal to 420. And next is 30x1 plus 40x2 plus 20x3 plus 10x4 less than equal to 800. So the basic approach is standard form of linear programming is minimum y equal to c1 x1 plus c2 x2 plus and so on cn xn subject to a11 x1 plus a12 x2 plus a13 x3 plus and so on a1n xn equal to b1. And next is a21 x1 plus a22 x2 plus a23 x3 plus a2n xn equal to b2. That is am1 x1 plus am2 x2 plus and so on amn xn equal to bm, where x1 x2 x3 so on xn greater than 0, b1 b2 and bm greater than equal to 0. So n greater than m. Handling of inequality constant. Case 1, select variables x1 plus 2x2 plus 3x3 plus 4x4 less than equal to 25. Modify 2x1 plus 2x2 plus 3x3 plus 4x4 plus x5 equal to 25. So x5 greater than equal to 0 is a slack variables. Case 2, surplus variables 2x1 plus x2 minus 3x3 greater than equal to 12. Then modified to 2x1 plus x2 minus 3x3 minus x4 equal to 12. And x4 greater than equal to 0 is a surplus variable. Handling of equality constant. If S is unrestricted, that is S can be positive or negative, then be set S equal to S1 plus S2 such that S positive greater than equal to 0, S negative greater than equal to 0. So example, maximum Z equal to x1 minus 2x2 plus 3x3 subject to x1 plus x2 plus x3 less than equal to 7, x1 minus x2 plus x3 greater than equal to 2, 3x1 minus x2 minus 3x3 equal to 5, and x1 x2 greater than equal to 0. It can be modified to maximum Z equal to x1 minus 2x2 plus 3x4 minus 3x5 subject to x1 plus x2 plus x4 minus x5 plus x6 equal to 7, x1 plus minus x2 plus x4 minus x5 minus x7 equal to 2, 3x1 minus x2 minus 3x4 plus 3x5 equal to 5, then x1 x2 x4 x5 x6 x7 greater than equal to 0. And now definitions. Definitions of feasible region denoted by S is the set of all feasible solution mathematically, and definition and optimal solution is a vector forms, that means x belong S subject to Z0 equal to CTX is maximum or minimum and where Z is termed by the optimal solution. Definition alternate optimal solution is a set x belong to S subject to all x belong to X has the same objective value Z0 and for all x belong to X and Z equal to CT X, Z minus less than equal to Z0. Next definition, if the solution set of LP contains only one element, it is termed the unique optimum. Next is, if the optimum value Z approaches to identify infinity, then the LP is said to be have unbounded optimum. The simplex method, minimum y equal to C1 x1 plus C2 x2 plus and so on Cn xn, subject to a11 x1 plus a12 x2 plus a13 x3 plus and so on a1n xn equal to b1, a21 x1 plus a22 x2 plus a23 x3 plus and so on a3n a2n xn equal to b2 and so on m1 x1 plus am2 x2 plus and so on amn xn equal to bn, where x1 x2 greater than equal to 0. Gauss-Jordan eliminations and artificial variable approach for the constant x1 x2 x3 and so on plus a1 m plus 1 x m plus 1 plus and so on plus a1s xs plus a1n xn, x2 similarly x2 x3 x4, then a2 m plus 1 x m plus 1 plus and so on a2s as xs plus a2n xn equal to b2, and then xm plus a bar m plus 1 x m plus 1 plus and so on a bar ms xs plus amn xn equal to bm bar. And our definition, a pivot operation is sequence of elementary row operations that reduce the coefficient of a specific variables to unity in the one of the equation and zeros elsewhere. In the above canonical forms, x1, x2, x3 and so on xm are termed the basic variables or dependent variables, where xm plus 1 and xm plus 2 plus and so on xn are called non-basic variables or the independent variables. The solution obtained from a canonical form is by setting the non-basic variables or independent variables to 0 is called a basic solution. A basis feasible solution is a basic solution in which the basic or independent variables are non-negative. So remark, number of basic solution equal to n by nm, which is equal to factorial n upon m factorial into n minus m factorial. Basic xi equal to bi, I equal to 1, non-basic xi equal to 0, and j equal to m plus 1 plus n. Definition property, a feasible basic solution is a simplex of the feasible region, where xv equal to x1, x2, x3 plus and so on xm, and cv equal to c1, c2, c3 plus and so on cm. Approach simplex method, start with an initial basic feasible solutions in the canonical form, improve the solution by finding another basic feasible solution if possible. When a particular basic feasible solution is found and cannot be improved by finding new basic feasible solution, the optimality is reached. Then an adjacent basic solution differs from a basic solution is exactly one basic variables. If one wants to find an adjacent feasible basic solution from one feasible basic solution, switch to another simplex which adjacent basic solution gives lowest objective functions. So derivations of the linear product rules, x1 plus x2 plus x3 plus and so on, a1 s xs equal to b1, then x2 plus x3 plus and so on, a2s xs equal to b2, and then xm plus ams plus xs equal to bm. Supposing one wants to replace one of the original basic variables with non-basic variables xs, we firstly increase xx from 0 to 1, then for all I equal to 1, 2, 3 up to m. Like this one, xi equal to bi minus ais, xs equal to 1, and for all j equal to m plus 1 up to n, and j does not equal to s, and xj equal to 0. Then theorem 1, inner product rule, z nu equal to summation of I equal to 1 m ci bi bar minus ais bar plus cs. Relative cost delta z equal to z nu minus z equal to cs minus summation of I1 m ci a bar is. Inner product rules, So moreover, one is in a maximization problem, a basic feasible solution is optimal if the relative cost of its all non-basic variables are all positive or zero. One should choose an adjacent basic solution from which the relative cost is minimized. Corollary: the alternative optima exist if delta z equal to 0. Given a non-basic variables x is changed into the basic variable set, then one of the basic variables x should leave from the basic variable set such that maximum x equal to minimum AIS greater than equal to 0 BI upon AIS. The above minimum happens at I equal to 1. Corollary: the above rules fails if there exist unbounded optima. Example: the LPP problems. Maximum z is equal to 6x1 plus 10x2 plus 9x3 plus 20x4 subject to 4x1 plus 9x2 plus 7x3 plus 10x4 less than equal to 600. Then x1 plus x2 plus 3x3 plus 8x4 less than equal to 420. Then 30x1 plus 40x2 plus 20x3 plus 10x4 less than equal to 800. Standard form: maximum f equal to 6x1 plus 10x2 plus 9x3 plus 20x4 subject to g1 4x1 plus 9x2 plus 7x3 plus 10x4 plus x5 equal to 600, g2 equal to x1 plus x2 plus 3x3 plus 8x4 plus x6 equal to 420, g3 equal to 30x1 plus 40x2 plus 20x3 plus 10x4 plus x7 equal to 800. And now tables like this one. CB ये हमने ले लिया 6, 10, 9, 20 और इधर बेसिस ले लिया 0, 0, 0. इधर x5, x6 and x7. These are the select variable. Then x1, 4, 9, x1, x2, x3, x4, x5, x6 and x7. तो x4 तक हमारे पास वेरिएबल्स थे तो उनकी वैल्यू थी 4, 9, 7, 10, 1, 1, 3, 8, 30, 40, 20 and 10. x5, x6, x7 में वही हम यूनिट मैट्रिक्स का यूज करते हैं 1, 0, 0, 0, 1, 0, 0, 0, 1. इसके बाद यहाँ पर हमने मैक्सिमम वैल्यू को चूज किया और उस मैक्सिमम वैल्यू जिस टेबल में थी इसको हमने जो है सेलेक्ट किया और सेलेक्शन के एलिमेंट्स जो थे उस कॉलम के उनसे कंस्टेंट को डिवाइड किया. जैसे 600 डिवाइडेड बाई 10 इक्वल टू 60, देन 420 डिवाइडेड बाई 8 विच इज इक्वल टू 52.5, देन 10 डिवाइडेड बाई 800 डिवाइडेड बाई 10 द इक्वल टू गेटिंग 80. सो द मिनिमम वैल्यू ऑफ दिस रो विच इज कॉल्ड पाइवट रो जिसमें एरो लगा हुआ है और ये आपका पाइवट एलिमेंट होगा. एंड अब हमें क्या करना है कि इस पूरी रो को 8 से डिवाइड करना है. जैसे यहाँ पर वैल्यू अगली कॉलम में जब भी आप अगली टेबल में जाएंगे तो 1/8, 1/8, 3/8, 1, 0, 1/8 एंड 0 इस तरह से हो जाएगी. इसकी वैल्यू चेंज करने के लिए आपको क्या करना है कि ओल्ड रो लेंगे माइनस पाइवट इसका 10 है मल्टीप्लाई करस्पॉन्डिंग वैल्यू. तो करस्पॉन्डिंग वैल्यू जो ये वाली वैल्यू है उसको मल्टीप्लाई करेंगे इस वाले पाइवट से और ओल्ड रो की वैल्यू से माइनस करके टू गेटिंग अनदर दिस रो एंड दिस रो. जैसे इसमें कैलकुलेट किया गया है और पूरे सिंप्लेक्स के अंदर एक ही मेथड हम फॉलो करते हैं अगेन एंड अगेन और जब तक आपके जो CJ की वैल्यू पॉजिटिव नहीं आती तब तक हम इसको करते रहते हैं. इस तरह से ये आपकी स्टैंडर्ड फॉर्म आई हैव ऑलरेडी एक्सप्लेन इट. This one and this one, then two phase method. स्टैंडर्ड फॉर्म से हम टू फेस मेथड पर जाते हैं. टू फेस अप्रोच मिनिमम x6 प्लस x7 सब्जेक्ट टू x1 माइनस 2x2 प्लस x3 प्लस x4 इक्वल टू 11, देन माइनस 4x1 प्लस x2 प्लस 2x3 माइनस x5 प्लस x6 इक्वल टू 3, then minus 2x1 minus x3 plus x7 equal to 1. So we generate the table this kind like as before और उसके बाद another table by using the phenomena or concept that I have already explained. और उसके बाद इसी तरह से देखिए यहाँ आप देख रहे हैं कि नेगेटिव वैल्यू जहाँ भी आ जाती है हम उसी को सेलेक्ट कर लेते हैं। अब यहाँ पर भी नेगेटिव है। एंड नाउ एग्जाम्पल मल्टी प्रोडक्ट मैन्युफैक्चरिंग। अ कंपनी मैन्युफैक्चर्स 3 प्रोडक्ट A, B and C. Each unit of product A requires 1 hours of engineering service, 10 hours of direct labor and 3 labor hours of material. To produce 1 unit of product B require 2 hours of engineering, 4 hours of direct labor and 2 hours of material. In case of product C, it require 1 hour of engineering, 5 hours of direct labor and 1 LB of the material. There are 100 hours of engineering, 700 hours of labor and 400 hours of material available. Since the company offers discount for bulk purchases, the profit figures are as shown in the next slide. This one, unit 10, 9, 8, sales unit 0 to 40, 40 to 100, 100 to 150, over 150. Here product B, sales unit 0 to 50, 50 to 100 and over 100. और उसके बाद यूनिट हमने यहाँ ले लिए प्रॉफिट के 10, 9, 8, वेरिएबल x1, x2, x3 एंड x4, देन वेरिएबल x5, x6, x7, सेल्स सी यूनिट की हो गई और उसके यूनिट यहाँ पर ले लिए, देन x8 एंड x9, देन x10. Formulate a linear program to determine the most profitable product mix. Like this one, let's denote the variables as shown in the table. Then we have the following: maximum Z equal to 10x1 plus 9x2 plus 8x3, 7x4, 6x5, 4x6, 3x7, 5x8 and 4x9. Subject to 1x1 plus x2 plus x3 plus x4 plus 2x5, x6, x7 plus 1x8 plus x9 less than equal to 100. Then 10x1 plus x2 plus x3 plus x4 plus 4x5 plus x6 plus x7 plus 5x8 plus x9 less than equal to 700. Then 3x1, x2, x3, x4 plus 2x5, x6, x7 plus 1x8 plus x9 less than equal to 400. So 0 less than equal to x1 less than equal to 40 and 0 less than equal to x2 less than equal to 600 and so on, and xn greater than equal to 0. And our sensitivity analysis, shadow prices. To evaluate net impact in the maximum profit if additional unit of certain resources can be obtained. Opportunity cost, to measure the negative impact of producing some products that are 0 at the optimum. The range of the objective functions, coefficients and the range on the RHS row. And our example, a factory manufactures 3 products which require 3 resources: labor, material and administrations. The unit profit on these products are $10, $6 and $4 respectively. There are 100 hours of labor, 600 hours of material and 300 hours of administration available per day. In order to determine the optimal product mix, the following LP model is formulated and solved. Like maximum Z equal to 10x1 plus 6x2 plus 4x3, subject to x1 plus x2 plus x3 less than equal to 100 for labor, 10x1 plus 4x2 plus 5x3 less than equal to 600 for material, and 2x1 plus 2x2 plus 6x3 less than equal to 300 for administration, and x1, x2, x3 greater than equal to 0. Then optimal solution and sensitivity analysis: x1 equal to 33.33, x2 equal to 66.67 and x3 equal to 0, z equal to 733.33, shadow price for row 1 equal to 3.33, row 2 0.67, row 3 0, opportunity cost for x3 equal to 2.67, ranges on the objective functions, coefficient 6 less than C1, 10 less than 15, 4 less than equal to C2, 6 less than equal to 10 and infinity less than equal to C34, less than equal to 6.67, 60 less than B1, 100 less than equal to 150, 400 less than equal to B2, 600 less than equal to 1000, then 200 less than equal to B3 less than equal to 300 less than equal to infinity. 100% rules, 100% rules of objective functions coefficient, which is equal to summation of delta Ci upon delta Cj less than equal to 100%. 100% rules of RHS constant, summation of delta Vj upon delta Vj less than equal to 100%. And now do it yourself. Question number 1. what is simplex method, how it is useful in research industry, and question number 2, what is two-phase method, explain it clearly. And that's it from session number 3. Thank you.